I'm Norman Wildberger, and in today's lecture we're going to start looking at the relativistic dot product, which is intimately connected with a very important chapter of 20th century physics, namely the theory of special relativity, introduced by Albert Einstein in 1905. This is a very interesting and sort of thought-provoking development in physics because relativity really transforms our understandings of the world around us and is very unintuitive and surprising, perhaps even shocking when you first learn about it. And when Einstein first introduced these ideas in the first part of the 20th century, most physicists didn't know how to deal with it, and it took a long time for the theory really to spread into the mainstream. Unfortunately, in modern pure mathematics, this theory really hasn't penetrated as much as you might have thought, and perhaps as it should. So young students, first-year undergraduates, for example, who are taking standard linear algebra courses, are often not exposed at all to Einstein's thinking, even though it actually fits very naturally with linear algebraic ideas, as I'm going to hope to show you today and in the next coming videos. Okay, so the theory of relativity, first of all, has a nice introduction here that I recommend to you. So at physics.unsw.edu, my friend Joe Wolf has put together a lovely series of videos and instruction called Einstein Light, and I suggest that you have a look at that if you're interested in the physics side of special relativity. So special relativity came about by people studying Maxwell's equation. There was a famous experiment called the Michelson-Morley experiment. Some important transformations that had been written down by Lorentz, studied also in some sense by Poincaré. And then Einstein came around and put these things together into this now celebrated theory. And there's all kinds of non-intuitive consequences of it that sort of mystify your average person, including things like time dilation, length contraction, this famous formula E equals mc squared, the whole notion of space-time, that we're living in a four-dimensional space-time, and that space and time really are somehow intimately intertwined. There are various so-called paradoxes or curious things that are hard to understand. For example, the twin paradox, that your twin could go off on a rocket ship and come back decades later and only have aged a fraction of how much you've aged. And then there's also practical applications of relativity, including the GPS system that many of us rely on, that our mobile phones use. And this, in fact, is very closely connected with both the special theory and the general theory of relativity involved in that. So I have actually given a lecture in the seminar series of my channel called The Geometry of Relativity and Why Your GPS Works. So if you're interested in the applications to GPS, you can have a look at that video. All right, so these are some of the ideas associated with special relativity. What we want to do is we want to have a look at things from a mathematical point of view, from this framework that we've been developing with regard to the dot product. And I think our treatment of this subject and our inclusion of it will really sort of distinguish this course from many other courses in linear algebra that you could take. We are looking at a new way of thinking about metrical structure from a linear algebra point of view, and I think this will have much to recommend at the point of view that we're going to take. And I'm hoping that other educators who are teaching linear algebra in other places will catch up and start incorporating some of these ideas, and in particular exposing their students to special relativity and the ideas coming from physics. So our aim is to introduce a mathematical framework for special relativity using linear algebra and a new kind of dot product. And our treatment is not going to require a prior knowledge of physics. So from my point of view, the mathematics of special relativity has an existence which is somewhat independent of the physics, very closely linked to it, but not logically dependent on it. And we're going to be looking at things just from the linear algebra mathematical point of view. And surprisingly, we're going to see that this framework really could have been discovered centuries ago. Okay, that we're going to see alternate ways that it appears in the world, not just in terms of relativity, but also, as it turns out, in planar Euclidean geometry when we're talking about the theory of circles. This is maybe a surprising, perhaps novel point of view that will, I think, shed new light on a lot of different things. All right, so our starting point. We're going to start with a two-dimensional vector space, just as we've been talking about in the last few videos. And we're going to introduce this new dot product. All right, so x1, y1 dot x2, y2 is now going to be defined to be the number x1 times x2 minus y1 times y2. Completely the same as what we've been discussing for the last few videos, except that there's a minus sign there instead of a plus sign. And I'm going to sometimes call this the red dot product if we want to distinguish it from the Euclidean one. And I'm going to, at least initially, put a little bit of red around that dot there to remind you that we are talking about the red dot product, and it's different from the dot product that we've been talking about before. We're going to also call this sometimes red geometry. So when I talk about red geometry, I'm talking about the geometry that's built up from this particular dot product. And our first exercise is to show that this is really very parallel to the Euclidean dot product we have been studying, namely that it defines a symmetric bilinear form. All right, so it's an exercise for you to check, make sure you convince yourself this is still a symmetric bilinear form. And if you don't know what that means, then it means that you have to watch the previous few videos, and I strongly urge you to do that. Okay, when we want to compare this new geometry with the one we have been studying, we'll refer to the Euclidean geometry built up from the Euclidean dot product as blue geometry. All right, so we're going to use as colors. Blue geometry for the Euclidean one, red geometry for this one. It will turn out later that there's a third color, another relativistic geometry called green geometry, which is closely related to the red geometry. And so the three geometries have a remarkable sort of triality that they respect. All right, so the consequences of introducing this dot product are what we're going to be interested in today. The first thing we're going to do is we're going to introduce the quadrants of a vector by exactly the same formula as before, that the quadrants of a vector is by definition v dot v. But in terms of coordinates, of course, it's going to look a little bit different. It's going to be x squared minus y squared instead of x squared plus y squared. And now we have the opportunity for a new definition. So not everything is the same as it is in the blue geometry here. There are some definitely different features. And one very important different feature is that we have this notion of a null vector in this geometry. We say that a vector v is null precisely when the quadrants of v is 0. In other words, when x squared minus y squared equals 0. For example, the vectors v equals 1, 1 and vw equals 1 minus 1 are null vectors. You see, if we take the dot product of this vector with itself, we get 1 times 1 minus 1 times 1. And here we get 1 times 1 minus 1 times minus 1. In both cases we get 0, so those are null vectors. We could have made this definition also in the Euclidean or blue case, but then it would have been rather trivial because there's only one vector whose quadrants is 0 in the Euclidean case, namely the 0 vector. Here we're getting some non-zero vectors whose quadrants are 0. That's very important, and these vectors are going to play a central role in this kind of framework. The next important notion, of course, is the notion of perpendicularity. So we're going to define two vectors v and w to be perpendicular precisely when their dot product is 0. So for example, the vector 1, 2 is perpendicular to the vector 2, 1 because 1 times 2 minus 2 times 1 is 0. Similarly, 3 minus 1 is perpendicular to 2 minus 6 because 3 times 2 minus minus 1 times minus 6 is again 0. And note that if we take a multiple of one of these vectors, say like 4, 4, then it happens to be perpendicular to itself. 4 times 4 minus 4 times 4 is 0. That's another way of saying this condition here. Quadrants of v equals 0 means that v dot v equals 0, which is saying that v is perpendicular to itself. So another way of thinking about what the null vectors are, they are the vectors which are perpendicular to themselves. This is a new kind of notion of perpendicularity. It's not geometrically the same, and we're going to have to get used to thinking about what it actually looks like. Okay, so let's have a look at our two-dimensional plane from this point of view. The vectors themselves are just as before. We have an x-axis and a y-axis, equally spaced coordinates on the x-axis, equally spaced coordinates on the y-axis. That's exactly the same. One thing now that we have that we didn't have before are these null vectors or null directions. So here is the line in the direction of 1, 1, and here is the line in the direction of 1, minus 1. We're going to draw these lines in red here very prominently, at least to start with. Alright, now let's have a look at some vectors that illustrate perpendicularity. This vector v right here and this vector w right here are perpendicular vectors in this red geometry. The vector v is 1, 2. The vector w is 2, 1. We've already seen that those two vectors are perpendicular. Note that they are sort of symmetrically placed with respect to this null line. If we reflect one of these vectors in this line here, in the Euclidean sense of reflection, then we would get that other one there. And in general, this is what happens. So if you take any vector AB, and you consider its reflection in the Euclidean sense in this line here, you get the vector BA. And AB and BA are always perpendicular vectors in this red geometry. What about the quadrants of V? Well, the quadrants of V by definition is V dot V. So that's 1 times 1 minus 2 times 2. That's a total of minus 3. So we get, of course, the possibility that the quadrants of a vector is negative. The quadrants of W is 2 times 2 minus 1 times 1, so that's 3. So here again is something that's different in this situation. We're having vectors whose quadrants is negative. It doesn't appear in the Euclidean story at all because x squared plus y squared is always positive. In particular, if we were trying to establish an idea of distance or length in this context, things would be more problematic because trying to take square roots is already very problematic even for positive numbers if you want to do it exactly. But for negative numbers it's even more problematic. In fact, relativistic geometry has been burdened by this inability to easily develop theories of angle and distance as is traditionally used in Euclidean geometry. That's one reason why relativistic geometry has not been developed at all as much as Euclidean geometry has, even though the physicists have been telling us that this is really a very important geometry. In fact, it's more the geometry of the world that we live in than Euclidean geometry is. So the physicists are telling us that. So what this really shows yet again is that ideas of rational trigonometry are all important to make progress in understanding geometry. That we really do not want to be talking about distance. We do not want to be talking about angle. We want to be talking about exactly this quantity here, the quadrants. And in a few more videos I'll introduce the rational analog of an angle, which is called spread. Okay, so in this diagram we've seen some perpendicular vectors. We've seen some quadrances. The vector u, which is minus 2, 2, right here, that of course is a special vector because it's a null vector. It's perpendicular to itself. And here I've shown you two more vectors, r and s, and r is minus 3, 1, and s is minus 1, 3. and you can check that those vectors are also perpendicular. So we get perpendicular vectors by essentially reflecting in the Euclidean sense in either one of the null lines. If we reflected this vector, say, in this null line, we would get a vector down here, which would be exactly the negative of this one. It would still be perpendicular to that vector. Notice that we express perpendicularity in the same kind of way as we do for right angles, with a little sort of rectangle there, but it's not a rectangle anymore, it's a little parallelogram. All right. So V and W are perpendicular, represented by that little symbol. R and S perpendicular, represented by that little symbol. All right, so now we come to the most important theorem in mathematics. Here now in this relativistic setting, in the red geometry setting. And the theorem has exactly the same form as it did in the Euclidean setting. Namely, vectors V and W are perpendicular precisely when this relation between the quadrants of V, the quadrants of W, and the quadrants of V plus W are satisfied. And I remind you of the proof. So here is exactly verbatim really the same proof as we had before, except now we have red dot products. And I see I need to make this one red as well. All right. So let's run over the proof quickly. Q of V plus Q of W equals Q of V plus W. That's exactly the statement that V dot V plus W dot W equals V plus W dot V plus W. And that's equivalent to what we get when we expand this thing out using the bilinearity. Then we cancel the V dot V and the W dot W's from both sides and get this equation. Then we use the symmetric property of the bilinear form to rewrite it as 2 times V dot W equals 0. Then we divide by 2 and get V dot W equals 0, which is equivalent to V is perpendicular to W. So exactly the same proof works, which is why that proof of Pythagoras' theorem is such a good one. And what does it mean? Well, what do right triangles look like? Well, they're just triangles, two of whose sides are perpendicular. We've just described what perpendicularity means. So for example, here's a vector V, which is 2, 1 again. And here's a vector W, which is now 2, 4. These two vectors are perpendicular because 2 times 2 minus 4 times 1 is 0. So we can express that perpendicularity with that little parallelogram thing there. So now if we take the vector V and then we put the vector W here, forming this triangle, this will have side V, that will have side W, then this green vector there is V plus W, which will be the vector 4, 5. So this triangle, what I've labeled 0AB, that one there that's shaded, is a right triangle in the red setting. Okay, it may not look like a right triangle in the usual framework. This is a right triangle in the relativistic setting. It's just as much a right triangle. But now the computation is different, but the Pythagoras' theorem is really exactly the same. The quadrants of V is 2 squared minus 1 squared, which is 3. The quadrants of W is 2 squared minus 4 squared, which is minus 12. So this quadrant plus this quadrant will be 3 plus minus 12, which is a total of minus 9. While the quadrants of V plus W will be 4 squared minus 5 squared, which is 16 minus 25, which is minus 9. So yes, indeed, the quadrants of 2, 1 plus the quadrants of 2, 4 is the quadrants of the sum of those vectors. And that's the algebraic equivalent to these two vectors being perpendicular. So make sure you understand this picture, and that perhaps you can make some other right triangles and practice checking that Pythagoras' theorem works. It's a theorem, and it's an important theorem in this red geometry. All right, so one of the things we did with a dot product in the Euclidean case is talk about linear functionals and lines and normals. Well, we could do the same thing here. The starting point is just the dot product between two vectors, and we can think of this as being a linear functional of w if v is fixed. So we think of v as being fixed, then this is a linear functional of w. And if we set it equal to some particular value k for a fixed vector v, then we get the equation of a line. That's a line with normal vector v. Let's have a look at an example. So v is the vector 3 minus 1. So here's 3 minus 1, say, that vector there. Then the corresponding functional will be this thing dotted with xy will be 3 times x minus 1 times y. So for a total of 3x plus y. So the lines 3x plus y equals k are the level curves for this functional. And they all have red normal, v equals 3 minus 1. Let's have a look at some of those lines. So here are our null lines. Alright, so if we want a vector that's perpendicular to v, we can get that by just interchanging the x and y coordinates. So the vector minus 1, 3, which is here, that vector up there, that's going to be perpendicular to v. And so the vectors which are perpendicular to v, or in other words those vectors for which the functional f of v is 0, give us this line right here. So that's the line which is perpendicular to the vector v. It has normal vector v, which happens to go through the origin. If we're looking at f of v equals 1, we're talking about the line 3x plus y equals 1 then, well, that'd be that green line there. So all the lines whose normal is 3 minus 1 are all lines which are parallel to this one. And the k value will determine whether it's 0 or 1 or 2 or 3 or minus 1, minus 2, minus 3 and so on. So you do have to get used to the perpendicularity being different, but once you do, the story is very similar to the Euclidean situation. So somewhat more generally, if we have a line ax plus by equals c, then a normal to that line in the red setting here that we're talking about, in this relativistic setting, is the vector a minus b. Okay, because this is really a minus b dot xy equals c. All right, now let's talk about projections. So the projection of w onto v, that's going to be given by exactly the same formula as we've seen several times now already. So it's v dot w over v dot v times v. Let's illustrate it in a situation. Here's vector v, which is, say, 3, 1. There's a line determined by v. Here's a vector w, which is minus 2, 1. Right? So suppose we're interested in the projection of w onto v. So we want to project this vector onto this line. And projection means the same as it does in the Euclidean setting. It's a perpendicular projection. We want to drop a perpendicular from this point to this line. But of course, perpendicularity here is in a different sense. It's got to be perpendicular to v. How do we get something perpendicular to v equals 3, 1? We go in the direction 1, 3. So this is a perpendicular direction to 3, 1. And that means when we drop the perpendicular, we have to go in this perpendicular direction to get down to the vector u. Right? So in this picture diagrammatically, this u will be the projection of w onto v. How about arithmetically using the formula? So the projection onto 3, 1 of the vector minus 2, 1, it's obtained by taking the dot product of this with this, divided by the dot product of this with itself, and that's all some number that gets multiplied by the vector 3, 1 that we're projecting onto. Okay, so what are these dot products? Here we have minus 6 minus 1 for a total of minus 7 in the numerator. In the denominator we have 3 times 3 minus 1 times 1 for a total of 8. get it all together, minus 7/8 of 3, 1. And is that what we're seeing here? Well, there's the vector v. Minus the vector v would be down here. It would be the vector minus 3, minus 1. And we can see that, yes, the u that we've chosen is pretty close to being minus v, but not quite. So minus 7/8 fits exactly with the picture that we've drawn. Now let's make an observation here that will be important. That in this formula for the projection, which of course is derived in exactly the same way as we derived it in the Euclidean case, because it only depends on the symmetric bilinear form properties of the dot product. In this formula, we have a denominator. And in mathematics, whenever you have a denominator, you have to worry at least a little bit about whether that denominator is 0. Okay, so if v dot v is 0, then this is problematic. It's undefined. So we really need this condition that v dot v is not 0 in order for this to make sense. That means that this vector v that we're projecting onto cannot be a null vector. So if we choose a vector v in one of these null directions, then this is an undefined quantity and the projection doesn't work. All right, now let's have a look at circles. So circles in this relativistic geometry look quite different from the circles that we're used to. So let's look at circles centered at the origin. And we have two different kinds of approaches to the circle. One is sort of the quadratic definition, the usual one, and another one is this more bilinear definition that I'm trying to get you to move towards in the Euclidean case. So what would be the analogs of those definitions here in this relativistic setting? Well, the formula is the same. V dot v equals k. That's the definition of a circle. Now, if v is the vector xy, well then v dot v is x squared minus y squared. So we get the equation x squared minus y squared equals k instead of x squared plus y squared equals k. And if we take the bilinear approach, well, we just replace this quadratic thing with two different vectors. Talking about the vector equation v1 dot v2 equals k, or in coordinates x1 times x2 minus y1 times y2 equals k. All right, how do we visualize things? Well, here's our two-dimensional plane. Here are our null directions. And I've now shown you some circles. Okay, so let's have a look at, well, the null lines first. Okay, this is a null circle. C0 is the pair of null lines x minus y equals 0 and x plus y equals 0. Because if we put k equals 0 here, the equation is x squared minus y squared equals 0. And that factors as this times this. So the solution to x squared minus y squared equals 0 is this pair of lines, exactly the null lines in red. So in this context, those null lines are a circle. They are in fact the circle of quadrants 0. In Euclidean geometry, the circle of quadrant 0 is singly the point of the origin. Here, the null circle is something non-trivial and plays a very important role in the whole theory. The other circles are all rectangular hyperbolas because they're of the form x squared minus y squared equals something. X squared minus y squared equals 1, for example, gives us the circle C1, which I've drawn here, which has two branches, one on this side, one on that side. Well, when k is minus 1, we get x squared minus y squared equals minus 1. We get the hyperbola opening upwards, so with two branches, right there. So these are very familiar hyperbolas from high school geometry. Here they're playing the roles of circles. Circles in this relativistic setting. And these pictures are really from the A1 definition. We're just relying on the quadratic definition for now. There's also a corresponding bilinear approach to these things, which I might talk about at some future point. But for now, I just want you to think of the circles in terms of their pictures quadratically, and here are the typical representative circles. If we replace the 1 with something else, well, then the rectangular hyperbolas are just dilated outwards or inwards, so we get the sort of family of hyperbolas like this, or like this, filling up the entire plane. And it's a lovely fact that pretty well any property of the circle in Euclidean geometry, pretty well, that you can think of, has an analog for these kinds of circles in this red setting. So we're really enlarging our view of geometry here, in some sense very simply, just by replacing a plus sign with a minus sign. And we're getting all kinds of information about something that's geometrically quite different. Okay, so time for some more exercises. Now, because we're getting on in this course, the exercises will become a little bit more substantial. And so these exercises are something that you can get your teeth into. Okay? It will require some careful thinking and possibly going back to the previous videos and seeing what we did in the Euclidean setting. Okay, the first one is to show that the quadrants from a point x0, y0 to this line ax plus by equals c is ax0 plus by0 minus c all squared over a squared minus b squared. In other words, what you get when you plug in x0, y0 into the equation, putting everything on one side, and then dividing by what's really the quadrants of the normal vector. The normal vector here is a minus b. So this is all in the relativistic setting. We're talking about relativistic quadrants from a point to a line. Okay? That means we're looking at the quadrants in the red or relativistic setting from this point to the line where we're going perpendicularly to the line. Next one, show that there are no equilateral triangles, even approximately, in this red geometry. So in Euclidean geometry, we can draw equilateral triangles, at least approximately. Actually, you need a square root of 3 to make things work exactly, but even without a square root of 3 over the rationals, you can draw approximate equilateral triangles. Show that in this case, you can't even do it approximately. And the last question is to come up with a parameterization of our circle C1, which, remember, was that rectangular hyperbola that looked like this. Given by this, e of t equals 1 plus t squared over 1 minus t squared, 2t over 1 minus t squared. And those of you who watch many of my videos know that I'm a very big fan of the rational parameterization of the unit circle, and I discuss that in many places. I think it's very important. So here what we're seeing is a variant on that, where we're parameterizing this unit circle, that's really what it is, in this relativistic or red geometry. And it's not that much different from the parameterization of the usual unit circle in the blue or Euclidean geometry. And you might also think about C minus 1, the other sort of unit circle of quadrants minus 1. All right, very good. So we've introduced this relativistic dot product. But for those of you who have not much experience with special relativity, you might ask, why would we consider this kind of dot product? It seems so unintuitive. It seems so different from our standard geometrical understandings. Well, in the next video, I'm going to show you a reason why this relativistic geometry is in fact very, very important, even if we don't consider relativity at all. In other words, purely from the mathematical point of view. In fact, purely from the point of view of planar Euclidean geometry, it turns out that this relativistic geometry plays a very important role. And this is not widely understood. It's probably more of a 19th century way of thinking rather than a 20th century way of thinking. But I'm hoping it's going to become a 21st century way of thinking. Okay, so very interesting connection between this relativistic geometry and the theory of circles, or more precisely the theory of oriented circles in the plane. We talk about circles with either an orientation this way or an orientation this way. So some classical circle geometry next time, and connecting and motivating this red or relativistic geometry. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.